So if you are watching this video, basically I did a second upload. So the third part of the video, basically I will talk about confidence intervals for sample mean. So let's look at what we call as the confidence interval of sample mean. Alright. Okay, so before that, when you look at hypothesis testing, so hypothesis testing, what you actually use is actually uses one parameter only. Usually that will be testing whether or not your population mean satisfies your null hypothesis or not. So what hypothesis testing usually do is just testing on one parameter, just uses one parameter to test the claim. So you might sort of like wonder whether or not this is a good enough test or not. So what confidence interval provides you is basically you try to specify some interval for which your population mean will fall into that particular interval with some confidence level or some confidence percentage. So what it means is if you sample your population many times and each time you calculate your confidence interval, you will find that your population mean will fall into that particular interval at a very specific confidence interval that you are calculating. So what confidence interval means is it basically specifies an interval for which your population mean is, let's say, alpha percent likely to fall into that interval. So if you sample it many times, you find that your population mean will lie into that interval. So what is the definition of population? What is the definition of confidence interval? Basically, based on this particular definition, you will guess that the definition will be something like, let's say, so because it is alpha percent, so alpha is in percentage, I need to convert it to the decimal version. So that's why I use alpha divided by 100. So based on this particular definition, confidence interval is the interval from A to B, for example, that your population mean, which is mu, will be fall into that particular interval. So this is the definition. So I'm going to show you how you can actually derive this particular equation. Okay, so let us begin with this. So this is the definition of confidence interval, and we actually want to find how do you calculate that particular interval. So this is a definition. Okay, so let us begin. So for sample mean, later on you will realize that it doesn't really matter whether or not this is sample mean or not. But right now, what we are doing is you look at sample mean, and you assume. Okay, so there are a lot of nuances. Usually, for calculation in confidence interval, you would assume that your sample mean has to be normally distributed. Otherwise, you can't really find your confidence interval. And by central limit theorem, as long as you keep that particular, what is it called? Keep that particular constraint, the sample size is big enough, for example, your sample mean automatically will follow a normal distribution. So this kind of assumption is used when you calculate your confidence interval. So your mu is your population mean, and your sigma is your population standard deviation. So for sample mean, we know that the population variance is given by sigma squared divided by n. Alright? So we want to test the sample mean, right? So the calculation of confidence interval usually begins by you asking a claim that you want to test, and those claims usually is through the samples. So what you actually want to test is this, which is a lot different from the definition of confidence interval. But as you see later on, I will arrive to that, so don't worry. So you start with this, and you know that because your sample mean, you can approximate it using normal distribution. So of course you want to use, for example, your z-score to sort of like find your confidence interval. And the idea of confidence interval is that this is symmetric around your mu equals to 0. Your confidence interval is basically a very symmetric kind of interval that falls between from minus C to C. And this particular shaded region will give you the confidence that you need. Alright? So when you convert it to the z-score version, this will become what I was drawing over here from minus C. So this is your x bar that you want to test. Let's say you know the population mean. Then you divide by sigma over square root n. That is your sample standard deviation. Alright? So immediately we can multiply from throughout the left side, the middle, and the right side with sigma divided by square root n, so that we can get rid of the denominator. So this is minus c times sigma divided by square root n. You have x bar minus mu. Then you have c multiplied with sigma divided by square root n. Alright. So now you want to get to that particular read blocks. So you minus x bar on the left side and the right side. So you have minus x bar minus c times sigma over square root n. And then you have minus mu. On the right side, you have minus x bar plus c times sigma divided by square root n. So you want to get rid of the minus sign. So in the end, you multiply everything with the minus sign. Then you need to change the direction of your inequality. So you have x bar plus c sigma divided by square root n. Mu, and then x bar minus c times sigma divided by square root n. So you rearrange the order because the right side has to be bigger than the left side. So in the end, you would get x bar minus c times sigma divided by square root n. And then mu x bar plus c times sigma divided by square root n. And what do we know about this? We know that this is the same as alpha divided by 100, your confidence level. So that's how you start from the definition and then slowly go towards the final answer. The final point that we want to calculate. So you might wonder, what is the value of C? The value of C comes from this particular diagram. So how do you find C? Okay, first thing first, your alpha percent confidence interval is given by this. Perhaps I write in interval notation. So later on you will see something very similar with another sampling method. The derivation is the same thing. Okay, so how do you find the value of C? C depends on your confidence interval. So if let's say, I think it's clearer for me to show it through exercise because right now you don't know all the values. So let's just go to the exercise. I've chosen two particular questions which requires you to first calculate the confidence interval, and then if let's say you are given the width of your confidence interval, how do you deduce back your percentage of your confidence interval? So let's look at question 5. You have a following data summarizes the total mass for a random sample of quail eggs. So n is 30, sum of x is 254.4, sum of x squared is 2271.6. Calculate a 99% confidence interval for the population mean. So immediately for the first part, what I would do is to use okay, 5a. Immediately you can calculate your x bar. Your x bar would be 254.4 divided by 30. So that gives you 8.48. So now there are a few things that you can do. Whether or not you want to use, okay, let's put it this way. So over here, you basically don't have any information of your population mean and your population standard deviation. So you need to use estimations. So what I would suggest is to use your x bar as your estimation for population mean. Then you use the unbiased estimate of population variance. So just use the formula. That will be 1 over 29. Then you multiply with 2271.6 minus 30 times 8.48 square. So this gives you 3.94. So now you know your mean and variance. What you can do now is to find the value of C. So remember just now when I draw the bell curve, your C is defined to be this way, right? So from minus C to C, that will give you 0.99, because for the first part you need to calculate 99% confidence interval. So the left side will be Z smaller than C minus, so the minus C part you need to reflect it to the right side. So that will be 1 minus PZ smaller than C. So this portion you need to understand how it works. Once you understand this portion how it works, then there's no problem. So this is equal to 0.99. So you have 2 times PZ smaller than C minus 1 is 0.99. So PZ smaller than C will be 1.99 divided by 2, which is 0.995. So refer to your refer to your table. You will find that C is 2.574. So once you find the C, you know that the confidence interval, so the 99% confidence interval is given by your X bar, which is 8.48 minus, sorry, let me just do it this way, 8.48 plus or minus C times your S square 3.94, because you are not given the population variance, so you need to estimate using sorry, I also need to do a square root. That's why you need to use the unbiased estimate of population variance. So this will be 3.94 divided by 30. Let me double check. 30. Yes, that will be correct. So once you have calculated that, you will find that the final answer is 7.55, 9.41. That will be your 99% confidence interval. So part B, if you are given the width, what is your confidence interval? So what is the width? The width basically is the largest number minus the smallest number. So let's say this is your confidence interval. We know that this is X bar plus C times sigma divided by square root n. This is X bar minus C times sigma divided by square root n. Right? So the width is basically this distance. So it means that the width of confidence interval will be given by 2 times C times your sample standard deviation. And in the question by itself, this is 1.3. So you can just substitute all the values inside. So 2 times C is the one that you need to calculate because C is related to the confidence interval. And then you have a bigger square root, 3.94 divided by 30 equals to 1.3. If you calculate this thing out, C is 1.794. So from the previous from our previous calculation, Pz smaller than C is equals to Pz smaller than 1.794, and you can read this from the table. This is 0.9637, but we are not done yet because you know that we need to find this part, and this particular equation can be broken down into this, which is why once you found this particular value, you need to use 2 times Pz smaller than 1.794 minus 1. That tells you what is your confidence interval. So this is 2 times 0.9637 minus 1, and you found that this is 0.9274. So therefore, this is a 92.7% confidence interval. Process is a little bit lengthy, but as long as you follow how I derive this particular set of equations highlighted in red, then basically you understand what I did was basically the reverse process of what I did earlier. So let's look at another similar question. Question 6. You are given the data, the following data. Calculate the unbiased estimate of population mean and variance. So for X bar, this will be 117 divided by 60, which is 1.95. For your unbiased estimate of population variance, that will be 1 over 59. Multiply with 232.72 minus 60 times 1.95 square. So this is 0.0775. I just use 4 decimal places. So that's part A. Part B, calculate 98% confidence interval. So the same thing over here, you need to find the value of C first, but this time I already know the equation, so I can directly quote the final line, which is given by the star. So I can directly just write 2 times Pz smaller than C minus 1 equals to 98% confidence interval. So Pz smaller than C will be equal to 0.99. So now let's find out what is the value of C using the table. That will be 2.326. This is reading from a table. So once you found the value of C, the 98% confidence interval will be given by your X bar, which is 1.95, plus or minus 2.326 times the square root of times the square root of 0.0775 divided by 60. So if you calculate this thing out, this is 1.8664, 2.0336. So now, part C. An alpha percent confidence interval for the population mean based on the sample is having the width of 0.118 kg. So you know that the width is 0.118 kg. So previously we already know that this is 2 times your C and then multiply with your sample standard deviation 0.0775 divided by 60 is equals to 0.118. So calculate what is the value of C. You found that this is 1.642. So then finally use this equation again, the equation in the star. So 2 times Pz smaller than C minus 1. So substitute the value of C inside, 1.642 minus 1. That will be equals to 2 times 0.9497. Just read from table. So this is 0.8994. Therefore, this is a 89.94% confidence interval. Of course, you can say that this is a 90% confidence interval. If you round it up, for example. Yup. So that's all for this particular video. So the next video will be the last section of this particular chapter, which is on confidence interval of sample proportion. After that, I will probably separate out my attention towards filling up the rest of the P3 and then P1 and S1. And then we'll also go into the passive questions. Alright, thank you.